Hi everyone, Assalamu alaikum. I am Maira Farman from Electrical Engineering Department, LAMS. The paper that I'm going to review is Nanoimprint Lithography. Before going to start, here is a short overview of my presentation. Firstly, I will discuss about the paper and then go towards paper continuation. I will talk about modern day applications of nanoimprint lithography to highlight its importance. Then we will discuss some limitations and disadvantages of nanoimprint lithography technology. After that, I will discuss the state-of-art approaches for nanoimprint lithography. Lastly, I will conclude this presentation for nanoimprint lithography. Here we will discuss about this paper. The term nanoimprint lithography was first coined in the scientific literature in 1996 by Professor Stephen Chow and his students published a report in Science. This paper is cited by more than 2,000 times because of remarkable work by Stephen Chow and his group as nanoimprint lithography is an efficient, low-cost, and high-throughput technology for replicating nanoscopic scale features less than 10 nanometers. In this paper, the research study of Stephen Chow and his students shows that the ultimate resolution of NIL could be 10 nanometer over an area much more significant than 1 square inch in an arising high resolution patterning method. The imprinting mechanism is repeatable and the mold is durable. The key advantage of this lithographic technique is the ability to pattern 25 nanometer structures over a large area with high throughput and low cost. Nanoimprint lithography over a non-flat surface has also been achieved. Imprint lithography is fundamentally different from micro contact printing. To pass a self-assembled monolayer of functional fluid onto the substrate, an elastomer stamp is needed, whereas in NIL it's different. Imprint lithography is more of a physical process than of a chemical process. Unlike conventional lithographic methods, imprint lithography itself does not use any energetic beams. Therefore, nanoimprint lithography resolution is not limited by the effects of wave diffraction, scattering, and interference in a resist and backscattering from a substrate. In the experimental setup formed by the author, silicon dioxide and silicon are used as the mold materials. Certainly, other materials such as metals and ceramics could also be used. Polymethyl methacrylate is used as the primary resist because it showed excellent properties for imprint lithography. PMMA has a small thermal expansion coefficient. More release agents are added into the resist and work well to reduce the resist adhesion to the mold. The pressure and temperature for the imprint process depend on the resist used. This article illustrates how imprint lithography can produce a single imprint with 25 nanometer feature size, 70 nanometer pitch range, vertical and smooth side walls, nearly 90-degree corners, and uniformity over 15 by 15 millimeter area. To compare the imprinted resist profile and profile of the mold features, the mold is examined with scanning electron microscope. Here is the scanning electron microscope micrograph of the mold that was used to imprint the PMMA strips. In this paper, the author proposed two basic steps. The first is the imprint step, in which a mold with nanostructures on its surface is pressed onto a thin resist cast on a substrate, followed by removal of the mold. This step duplicates the nanostructures on the mold and the resist film. In other words, the imprint step creates a thickness contrast pattern in the resist. The second step is the pattern transfer, where an anisotropic etching process, such as the resistive ion etching, is used to remove the residual resist in the compressed area. This step transfers the thickness contrast pattern into the entire resist. During the imprint step, the resist is heated to a temperature above its glass transition temperature, uh, and at that temperature, the resist, which is thermoplastic, becomes a viscous liquid and can flow, and therefore can be readily deformed into the shape of the mold. The resist viscosity decreases as the temperature increases. Here is the short video on the working of nanoimprint lithography technology.
Slowly peeling it off, we see that the structures are still in the stamp, and there's also structures on the imprinted substrate. And here we can enjoy our very nice imprint with good result.
Um, Here are some scanning electron microscope micrographs of 30 nanometer wide metal gratings with a 150 nanometer period fabricated using imprint lithography and lithotraphy process. To examine the uniformity of this process, arrays with 30 nanometer wide strips and a 150 nanometer pitch were fabricated at the four corners and the center of a mold that had a size of 15 millimeter by 15 by 18 millimeter. After imprint lithography in PMMA, lift-off process left 30 nanometer wide metal lines with a 150 nanometer pitch on the substrate. As the figure clearly shows, that imprint lithography can be very uniform over a significant large area. Here are some modern day applications of nanoimprint lithography. NIL has been recognized as essential components in the various fields of solar cells, optoelectronics devices, nanoscale sensors and actuators, high density magnetic disks, biological devices, microfluids, in the future manufacturing. Nanoimprint lithography is the parallel patterning method to fabricate biological microarrays, which will boost the biotech devices sensitivity and accuracy. NIL-based Capillary electrophoresis tests for DNA separation, nano-electrochemical transducers for biochemical sensors. 10 nanometer nanofluidic channels were developed using NIL technology and were used for DNA testing. NIL is used in semiconductor devices. In recent years, ultraviolet tunable NIL technology has been used for advancing integrated circuits. NIL is used to make MOSFET and memory devices. It is also used to control of polarization, color, media for hard drive, disk drives. Here are some limitations for nanoimprint lithography technology. There is a lack of flexibility, which is a common limitation of nanoimprint lithography techniques. The adhesion between mold and resist is a significant problem because the mold and patterns may be broken during the procedure of mold release. The currently crucial challenges for NIL include overlay alignment, template fabrication, defect control, high yield, and seeking especially suitable application fields. Nanoimprint lithography emerged into an attractive pattern technique and developed considerably in terms of material, process technology, and equipment. In the recent years, another technology has proven a wide range of capabilities, leading to its recommendation as a production suitable alternative lithographic method. Particularly soft ultraviolet NAL is a very flexible and efficient technology capable to a large variety of structure, size, and shape, including complex shapes and 3D patterns without compromising mass manufacturability. Nowadays, ultraviolet NIL is the method of choice for various emerging applications due to the maturity of the technology and its compatibility with the semiconductor manufacturing environment. Laser-assisted nano-imprint lithography to pattern nanostructures on various polymers within a short heating and imprinting time. Therefore, LADI is a good tool to pattern the nanostructures directly without etching, especially for metal materials. This novel method can overcome the patterning problem for the hard solid-state metal materials, and the imprinting time is just within hundreds of nanoseconds. Here's the conclusion of my presentation for nanoimprint lithography. Currently, NIL technology is one of the most successful technologies that are being used commercially for the fabrication of structures at the nanoscale. Due to its economic aspect and mass fabrication capability, NIL technique has been explored continuously to fabricate devices at both academic and commercial platform. NIL aims to meet the different application requirements, namely the nanostructures or device fabrication. NIL applications mainly cover nanoelectronics, nanooptoelectronics, nanophotonics, nanobiology, and optical components, etc. Thank you for being such a wonderful audience.